Welcome students. In our today's lecture, we will study topic number 1.11 electric dipole. Now you can see the figure. Here in this figure there is a negative charge and there is a positive charge. These two charges, they are separated by distance twice of a. Here you can see that the magnitude of the charge is same. Here also it is q and here also the magnitude is q, but their polarity is different. One is positive and the other is negative, and that's why the word dipole is there. Di means two. So this electric dipole is a system of two opposite charges which are separated by distance 2a. So now we can define an electric dipole as it is a pair of equal and opposite point charges q and minus q separated by distance 2a. Now a new physical quantity called electric dipole moment can be defined as P is equal to Q into twice of A. This electric dipole moment P is a product of a charge and the distance between the two charge. That is, you can see here magnitude of any charge. There are two charges. So this dipole moment P is nothing but the magnitude of any charge and the distance between them. This electric dipole moment P is a vector quantity and its direction is always from negative charge to positive charge. Students, remember that electric field is always from positive to negative, but the direction of dipole moment is from negative to positive and it is along the line joining the charges. Now let us see some important points related to electric dipole. First point is the direction of the dipole is taken from negative to positive. You can see from the figure also that the direction of a dipole moment is from negative to positive. Next is the net charge on an electric dipole is 0, but its electric field is not 0. Net charge of a dipole is 0. Why? Because you can see here a dipole is made up of one negative charge and other positive charge. So overall total charge will cancel out, because if we'll add these two charge then the result will be 0. So total charge of an electric dipole is 0, but the electric field of this dipole is not 0, because we know that electric field will emerge from positive and move to negative, so there will be electric field. It is not equal to 0. electric field of a dipole will be like this. And so around a dipole there exists electric field. Then next point is about SI unit. SI unit of an electric dipole is coulomb meter. Now student, earlier also I told you that whenever we have a formula of any physical quantity, we can get unit as well as dimensions easily. So here also the formula of electric dipole moment is P is equal to Q into twice of A, and we know that the unit of Q is coulomb. So we will write for Q coulomb. And what is twice of A? It is the distance between the two charge, and the unit of distance is meter. So coulomb into meter. So unit of an electric dipole is coulomb meter. Next point says that for a single charge, electric field falls according to 1 upon r square. We know that if there is a single charge particle Q, then the electric field due to this charge at any point P, which is at distance r, is given by E is equal to K Q by r square. Means the electric field decreases with distance according to 1 upon r square. But for an electric dipole at a large distance, this electric field decreases according to 1 upon r cube. You can see for a single charge it is related with 1 upon r square, and for an electric dipole it is related to r cube. Means for an electric dipole, electric field decreases rapidly with distance compared to a single charge. Here see the power is 3 and here the power is 2. So here the decrease will be rapidly. Now let us see how would be the electric field of a dipole. Now here we can find the electric field of a dipole at any distance using Coulomb's law and superposition principle. We have already used Coulomb's law earlier also. Also we have used principle of superposition in our earlier topics. So here also, to find the electric field of a dipole, we have to use both this Coulomb's law as well as principle of superposition. Now students, we know that an electric dipole is made up of a positive charge and a negative charge, which are separated by distance 2a. Now here an imaginary line passing through both this charge is called an axis of a dipole. See this line which passes through both the charges. This is an imaginary line. which is called axis of a dipole, and the other line which is perpendicular to the axis and passes through the midpoint of a dipole is called an equator of a dipole. So remember these two lines. One is axis of a dipole and the other is equator of a dipole. Now we will find the electric field on the axis of a dipole and also electric field on the equator of a dipole. So now first we will find electric field on the axis of a dipole. Now students, you can see the given figure. In this figure, a dipole is there having a positive charge and a negative charge. The separation between them is twice of a, and you can also see a line passing through both this charge, which is an axis of a dipole. See, we have taken only one side. The same thing can be imagined on the right side also. So here we have taken a point P which is at a distance r from the center of a dipole. You can see this is a dipole, and here we have taken a point P which is at distance r from the center of a dipole. And now we are going to find an electric field at this point P. So we know that the electric field at this point P will be due to this positive charge also. Also, the electric field at point P is due to this negative charge also. So, electric field at point P due to positive charge is given by E plus. So now first we will find the electric fields at point P due to positive charge as well as due to negative charge by using Coulomb's law, and then we will add these two electric fields. In figure you can see that point P is at distance r from the center of a dipole, but this point P, its distance from charge Q will be this much, that is, this distance of point P from this charge Q will be R minus A. From the center of a dipole, the distance of positive charge will be A, and this distance is R. So, distance of point P from positive charge Q will be R minus A, that is this much distance. And so the electric field due to this positive charge can be given as E plus is equal to K Q by distance square. We have already studied the formula for electric field. And so here the distance of positive charge is r minus a, so it is this. Similarly, the electric field at point P is due to negative charge also, but here the distance of this charge from point P is r plus this much distance, and this much distance is a. So the distance of negative charge will be r plus a. So here also we can write the formula for electric field of negative charge as E minus is equal to K Q upon distance square. But here the distance is r plus a. Now electric field due to positive charge is E plus, while electric field for negative charge is taken as E minus. As the charge is negative here, minus sign is taken out. We know that value of K is 1 upon 4 pi epsilon naught. So after obtaining the electric field due to both the charges, now simply we have to add this electric field using superposition principle. So total electric field E is electric field due to positive charge plus electric field due to negative charge at point P. Now we will put both the electric fields, and we can see that in both K and Q are common. You can see KQ here also, K and Q here also. One more thing, unit vector P for the direction of electric field here also, and it is here also. So we can take these things common. So you can see I have taken K and Q common here and P here. So inside the bracket these two things will remain. 1 upon r minus a square and 1 upon r plus a whole square is inside the bracket. You can see this here. Now after simplification, see, you have to use simple mathematics to simplify this, and after using that mathematics you can easily get this. Now we know that electric dipole moment P is equal to 2aq. So here also you can see there is q, there is a, and here 4 means it is 2 into 2. So you can get 2a and q. In place of this 2aq you can put p. So next step from this formula is like this. In place of 2aq we have written here p, and so we get this formula. So this is the general formula for an electric field on the axis of a dipole. Now if we consider point P at a very large distance, that means this point P is at a very large distance from this dipole, then compared to this distance A, this R will be very greater, and if this R is greater compared to A, we can neglect the distance A as R is very large. So in above formula, if we'll neglect this A, then our new equation will be this. Simply take A is equal to 0. So for a far away distance from a dipole, the electric field can be given by this simple relation, and generally this equation is widely used. Students, simple mathematical steps I had left for you. From this step to this step, from here to here, you can easily do by using simple mathematics. Now, next we will obtain electric field of our dipole on the equator. Now, to find electric field on an equator, we know that a dipole, its midpoint, and a line passing through the midpoint which is perpendicular to the axis of a dipole is called equator. And if we'll choose any point here to find electric field, then the distance of this point, suppose P, from this charge will be this much, positive charge, and from negative charge the distance is this much. You can see here the distance of point P from positive charge and from negative charge is same. This distance is twice of A, and so this much distance from the center will be A. Here we have taken this point P from the center which is at distance R. So by using Pythagoras theorem, you can get this distance. As this is R, this is A, this distance will be root of A square plus R square. So this concept we are going to use to find the electric field on the equator. Now students, you can see the given figure. Here a positive charge is there, a negative charge is there. Distance between these two charge is twice of A as usual. From the midpoint of this dipole, this is an equator, and a point P is taken at which we are going to find the electric field. Here this plane is given only to get the three-dimensional effect. Electric field due to positive charge at this point will be in this direction, denoted by E plus, electric field due to negative charge at point P is towards this negative charge denoted by E minus. So first we will find this E plus and E minus again by using Coulomb's law. So for this electric field E plus, we get two components, one along the horizontal line, that is along x-axis, and the other along y-axis. Similarly, for E minus, we get two components. See, this is E minus. We get one component along the x-axis and the other component along the y-axis. Now the components along the y-axis, that is this two component, will cancel out and only the x component will remain. So here mathematical steps will be like this. So E plus is given by K Q by distance square. We know the distance is root of a square plus r square. So its square will be this, and the components are this two. This will be the x component and this will be the y component. Similarly, electric field due to negative charge, its x component and its y component, these things are same. Now you can see here there is a negative sign because y component of electric field due to negative charge is towards downward. Here the positive is because the y component is towards the positive y direction, while the x components for both the charge is towards positive sides. So here these two components are positive. So these two equations are obtained by using Coulomb's law, and then the resultant electric field can be obtained by addition of these two electric fields. So by superposition principle we can add this, and using simple mathematics we get this relation. Now from the figure, cos theta is a upon r square plus a square raised to 1 by 2. Using this value of cos theta in this equation, we get this step, and then putting twice of a equal to p as earlier, we get this relation. Now students, the mathematical steps are same as earlier. Here only you have to take care about the components. Now if we take this point P at a large distance, you can see here this point P is taken at this distance, but if it is taken at a large distance, then this formula, which is obtained here, we'll take the simple relation. Earlier also we have did this. At a large distance we can neglect this a square. So considering this a is equal to 0, we get a simple relation which is used very widely. So finally we can obtain the electric field at the equator of a dipole.